Hello again. Well, we just finished breadboarding the Winky Blink circuit, and here's its little friend, the siren circuit. And the siren goes through and makes a lovely annoying noise for us. And I want to go through and use this as a little bit of a breadboarding exercise, and I know I've set you guys up to try it on your own, but I do appreciate that this one's a bit more complex. There are going to be a few more things going on, so I thought, well, maybe I'll provide you a few answers. So here's some ideas for breadboarding the siren circuit if you have to go about doing that. First of all, have your breadboard ready so that you're all ready to go. Second of all, sort out all of your components. You've got a lot of components and you want to make sure you've got the right ones. I'm just going to go through here and do a quick little inventory of what we've got and talk about what the different parts do. Okay, now this power supply down here is going to be plus 9 volts. So you could use a 9-volt battery or you could use a power supply. And somewhere in your supplies you should have a 9-volt battery clip kicking around. And anyways, it's the thing that looks like it fits onto a 9-volt. I'm not sure why I don't have mine here. Probably because I'm planning on using my power supply to make this work. So anyways, if you've got a power supply, set it to 9 volts. If you're running off a battery, a 9-volt battery should work fine. Probably a 6-volt battery would work fine too. And your power is going to come in right through here. And this is going to be the positive side of your circuit right up here. And as I usually lay out my schematics, the electricity is all going to trickle down here to the ground side, or it's going to come around back to the battery and come back in here because the electricity always needs to make a full loop while it goes out into the circuit. Okay, so the first thing it comes into is the on-off switch. And if you're running this off of a power supply and mounting it up on a breadboard, you probably don't really need an on-off switch. This is more set up for people who are going to be designing this as a printed circuit board, and you don't always want your 9-volt battery to be dying. If you're on a breadboard, you can always just unplug the battery. Works pretty good. But let's take a look at this because this switch that I've put into some of the kits is a little bit different from some what you might be expecting, and it's not exactly the same one that shows up in the schematic right here. So there's a number of different types of switches that we can use in electronics, and I just want to talk about what some of them are. So I'll just move my components over there for a moment. And the most common switch that you'll see drawn is just like we have right there. And it'll look like this. And this will be a simple on-off type of switch that we call the SPST. And that's short for single, lovely G there, single pole, single throw. So the SPST switch is a single pole, single throw switch. And what that means is you've got one input and it can only go out one possible output. Single input, one possible output. Okay, what we've got in our kit is something called the SPDT. Those of you who are playing the home game are going, gee, that looks like a double throw. So single pole, double throw. And what that means is I've got a single pole, one input coming right here, but I can throw my switch to either of two different positions. And so on a switch like that, like you'll see in our cases, usually what you'll see if you look at the bottom of the switch, there'll be 3 leads coming up from the switch, about like so. We've got 3 wires coming off of ours. Okay, and what happens here is this one right here is always the middle one. Okay, so when you throw your switch, you can connect the middle one to the one on that side, or the middle one to the one on that side. So in a single pole double throw switch, if you use it as just an on-off switch, you can get away with that. Just ignore that extra side. And now if you throw the switch this way, you have no connection here. And if you throw the switch that way, you do have a connection. So you can use a single pole double throw as a single pole single throw. In other words, you can use this thing as that thing by simply not connecting to that bit. We use all the big words here. Alrighty, so that's a single pole double throw switch. Sometimes you'll see it's big brother or sister, the double pole double throw switch, where you'll have 6 leads coming off the back. More like so. And, of course, these have, a little switch down on the front right there. Should have drawn that in. There we go. And, oh, here we go. Don't know why you couldn't see it. I could see it perfectly fine. So here's our double pole, double throw switch. And this is actually 2 single pole switches basically glued together right down the middle. Okay, so the schematic symbol for a double pole double throw switch is you've got 2 inputs right here. Now they're independent inputs. These are 2 completely separate switches. Electrically, the only thing that they have holding them together is a mechanical switch. So when you slide one in one direction and one in the other direction, both switches throw back and forth at the same time. And I'll talk about why you might want to do that in just a minute. There we go, slide that up here. So our schematic for this one is there's a single pole double throw switch. Give myself a bit more space there. There's another single pole double throw switch, and then you'll see a dashed line joining these together, meaning that when you throw this one this way, the bottom one also has to slide down that way. So this would be useful for something like a stereo system. So if you had your left channel audio and your right channel of audio, and you wanted to switch it to headphones, okay, or speakers, okay, this one might go to your headphones, and this one might go to your speaker, okay. And so if you want to switch both your channels at the same time, you only have to throw one switch and it goes that way. There's all sorts of different things that we can use these switches for, and they're really useful. But these are some of our most common switches. I'll talk about the push button switches in just a moment. They're slightly different, but we've got a single pole double throw in our kit, or at least we do in 2020. I might give you something different in the future. And we're going to ignore one of those pins on it, and we're going to use it as a single pole, single throw, or a simple on off switch. When you close that switch, electricity can get through, and when you don't, it cannot. So let's just take a look at that, and there we go, bring that back in, and there is our single pole double throw switch. We're going to ignore one of those pins when we go plug it in, and we'll just use it as an on-off switch. Okay, coming around the top right here and just looking at our components, this transistor right here, you'll notice that it points in proudly. Notice the emitter is on this side of this transistor. Okay, the emitter is always the one with the arrow. And in this case, it is pointing inwards proudly, meaning that it is a Pnp transistor. And if you look at your parts list down here, the PNPs that I use in my shop are a 3904 transistor. Now they look almost identical to the 3906s, so you really have to take them and take a good look at that flat side and tilt it back and forth until you can see the shiny text on there that says 3904, sorry, 3906. Make sure it doesn't say 3904 on there. And there we go. I'm not sure if that's going to show up on the computer screen or not, but I can clearly see that it says 3906. In fact, it said 2N 3906, which is the full part number of what we want. Okay. I'm going to come back to R2 in just a moment. I'm going to come along here and talk about our momentary push button switch, because there's also a whole bunch of different momentary switches that we can get. And this is a nice one right here, but we've also got some other nice ones in your bag of goodies that I gave you. And this switch right here is indicated with a symbol like a little hat over top of it. Now, there's your push button, and when you push that down, the arrow's not part of the schematic. When you push that down, that connects there to there, but when you let go, it springs back up. Now, there's also a number of different switches that you can get that all kind of look the same, because there's also one that looks something like that is how I draw it in the schematic. Other people just use one standard schematic. But you can see the difference on here is that when you push down on it, this one's going to open the circuit, and when you push down on this, this one's going to close the circuit and allow the electricity to go through. So we call this switch that we've got right here normally open, and we call this one normally closed. Okay, of course, it's electronics, so we abbreviate that to NO and NC. So this is a push button switch that's normally open. When you push on it, you close those connections and it joins together. The other thing is that you can have either a momentary switch like this one, that when you click it, it pops back up right away and opens up again, or you can have a latching one that stays down. So we want on our circuit to use a momentary. You have to keep it pushed down. Okay, so there we go. We've got a couple of different switches. Now these ones fit really nicely into a breadboard, but I've also given you in your package some smaller ones. And these ones almost fit really nicely into a breadboard. In fact, the little ones are much easier to use sometimes, because when you fit them into the breadboard, they're much easier to fit just because they take up less space. But I find that because their legs are a little bit shorter, the little ones don't stick into the breadboard nearly as well. However, they both work the same way. They've got 4 legs on them, and if you hold them up and down so that you're kind of looking at them about like so, there's our big button in the middle, and you'll have a leg come off this side and a leg come off that side, leg come off that side. These 2 legs are actually connected to each other inside the switch, and these 2 are connected to each other inside the switch as well. So you can just draw a line connecting those 2 right there in your brain and say whatever voltage you have on that button, you also have on that button, or pin, I should say. Whatever you've got on that pin is also on that pin. Whatever's on that pin is on that pin. And your switch is actually right in between them. So if we look at that as our schematic, okay, there's our schematic coming in right there, and the switch goes across that way. And it's really easy to get that turned around and put it on your board at 90 degrees. It fits beautifully on the board. And I managed to do that in another video that I was filming and didn't notice until I was all done filming the video. And I was not a happy camper when I realized that. So anyways, pay attention to the orientation of these little switches. And if you can get this one to fit into your breadboard and you want to use it instead, you know, it's a nice little one. In fact, you'll see these used on a lot of circuit boards where you have handheld gaming units or something like that, and there'll be a plastic button on the top that's all fancy labeled and marked, maybe has some lights on it or something like that. But that'll be a little switch like that'll be mounted down on the board inside, and all your big fancy plastic button is doing is going down inside the case and pushing on the little button. So there we go. Momentary, normally open, push button switch for S1 in there. And just watch that orientation when you go to put it in. Let's see, we've got R4 coming down right in here. Now in your spec sheet, it says that R4 is supposed to be a 22K ohm resistor, which in my case is red, red, orange. So I do have a 22K ohm resistor. But really, for this one, anything between about probably 10K and 47K would work fine. Maybe 10K to 100K would actually work okay for this resistor. Really, the function of this resistor is when you push your button down, this resistor slows down how long it takes to charge C3. So generally C3 will charge really, really quickly, but a bigger resistor here will make it charge a little bit slower. So you can actually play around with those values quite a bit. And in some ways, you don't even really need a resistor there, but hey, it's in the circuit, so we're not going to mess with it. And then we come down to C3 right here. And again, C3 is a polarized aluminum electrolytic capacitor. Make sure you pay attention to the negative signs and the stripe written on the side of the capacitor right there. There we go. There's that negative sign. And anyways, the negative side, when we hook it all together, of course, is going to be going down towards ground because our positive will be on that side. Now, what's going to happen in our circuit is when we push this button down, this resistor is going to slowly, not so slowly, but slowly, allow this capacitor to charge. And when this capacitor is charged, it's going to activate the circuit and start making noise. These two resistors right here, combined with our NPN transistor in the middle, are going to drain this resistor, and that's going to, drain this capacitor, discharge it, and that's going to give us our sound as this capacitor slowly discharges into the circuit. So a little later on, after we breadboard, I'll be talking about this point right here being this point right here being a really important test point to see if you've got the first part of your circuit working okay. All right, in here we've got R1, which is a 120K ohm resistor, and probably anywhere between, something close to 100 and something up to about 200 would work in there. But if you've got 120, it works pretty nicely. And down here at R3, we've got our 47K ohm resistor. So on my board, that's yellow, violet, orange right on there. Okay, so we've got a few resistors. This is a not pointing in transistor, so it's a different type of transistor than we have on the other side of the board. You don't want to get them mixed up because it won't work. So this one's not pointing in, and again, our arrow for our emitter is on this side now. Now, because I've chosen a 3904 and a 3906 as the transistors for this circuit, they are both emitter, base, collector, or big cookie transistors. So it's easy to remember what the pins are. Coming around this side here, we've got a small capacitor that's a little different than things that you may have used before. And it lists that in the instructions as being an 18 nanofarad capacitor. I have updated that to say 22 microfarad. You might see some that say 18. Really, you can play around with a few different values in here. This capacitor is going to connect from this transistor over to the base of this transistor, which will feed back into this transistor and create this little feedback loop that's going to vibrate back and forth. And that's going to control the frequency of the sound coming out of our speaker. So playing around with a different capacitor in here, probably anywhere from 10 nanofarads up to 100 nanofarads would get you different sounds right in here. We've got 22 And maybe we'll try changing things up with it a little bit later on. Now, what am I talking about when I say nanofarads? It's, if you're not familiar with your metric prefixes, the nanofarad is going to mess you up. And we do spend a lot of time talking about metric prefixes in electronics. So let's just go over some of the ones that we really commonly know. Like everybody's familiar with the kilometer, right? km. Okay, and we know that a kilometer is 1,000 meters, okay, or times 10 to the 3. And then we know what a meter is, okay, 1 meter. Well, then we come down, and if we go smaller than that, your next step down, don't say centimeter. The centimeter, not really an official unit. It's only multiplied like by 1/100th. The official unit, according to engineers, is the millimeter. The centimeter was just created for people who missed inches. So anyway, you can use centimeters. I don't mind. So long as it's metric, we're all good. But the millimeter is our next unit down, and that's 0.001. You can see that I've moved the decimal place 3 spots over to get to there. And now I've moved the decimal place 3 spots over to get to right there. And so this is times 10 to the 0. This is times 10 to the minus 3. Okay, if we go a little bit smaller than the millimeter, we get the micrometer. And since we've already used an M, the people who are coming up with metric didn't know what else to do. So they said, oh, we've got, like Greek letters and the fonts on our typesetters, or did they have typesetters back when they were coming up with metric? We know how to make a U, or more correctly, a mu. Mu is the Greek letter that looks like our U right here. So it actually kind of made sense if you were a Latin speaking scholar back in the day that you'd say, oh, well, we've used up the M. Let's just use the Greek M, mu. So the micron, or the micrometer is a good way to describe it, is 0.000001, or times 10 to the minus 6. And after that, you go milli, you go micro, and then you go nano. So when you're getting down to like wavelengths of light and things like that, you're getting in here. And each time I do this, I just move 3 decimal places over. And because the farad that we use to measure capacitors, the farad is a really, really large unit, we actually go down all the way to picofarads. And if you had a picometer, it would be times 10 to the minus 12th. And I'm not going to write all those zeros because my pencil's getting dull. But when we're looking at a nanofarad, okay, we're looking at a number that is, so 22 nanofarads equals 22 times 10 to the minus 9th farads, or 22 billionths of a farad. So it's pretty tiny, but keep in mind that even our big capacitors are all measured in microfarads, so they're millionths. So this is only a little bit smaller. Well, okay, million times smaller, but smaller. So that's what we're looking at. Now, you'll identify that one because on the side of it, it will say 2, 2, 3. Now, capacitor identification can actually get quite frustrating sometimes. It's really nice with the big aluminum electrolytics that it's written right on them. But where I'll show you in just a minute where it says 223. And what that means is 22 times 10 to the 3 picofarads. Since picofarads is the smallest size of capacitor that we use, we're going to measure all of our units in picofarads, and 223 means 22 times 10 to the 3 picofarads, or 22,000 picofarads. And as you can see up here, if you go from pico up to nano, that's a step of 1, 2, 3, 22. Oops. nanofarads. So 22,000 picofarads is the same as 22 nanofarads, or it could be 0.022 microfarads. Easy. It's just metric. Move things 3 decimal places that way, move them places that way. You already know how to do it for kilometers and meters and millimeters. All we've done is added a few more tiny little things in there to describe our capacitors. So let's just take a look at that capacitor right there and see if we can zoom in on it and see where that 223 is. There we go. Come right in there. And oh, great, the light's blaring on it. Let me just turn that off. You know, that actually looks nicer with the light off. I might try leaving it off for a while. So there you can see right on there it says 223. And then to make things a little more complex, they throw a K on the end. You know, it's like people read that and they instinctively say, oh, that's 223,000 because they know that a K means 1,000. The K has nothing to do with the value of the capacitor. It's not part of the number. It's there. It's basically the equivalent of the tolerance band on the resistor. It's telling you how accurate this capacitor is going to be. For all intents and purposes in high school electronic shops, you can mostly ignore that. Ignore the K. On capacitors, just look at those 3 numbers and you'll be good. Okay, let's keep moving along right here. And up at the top, we've got R2, which is a 100. Oh, I forgot, we're really zoomed in there. Up at the top, we've got R2, which is a 100 ohm resistor. And that 100 ohm resistor, if you don't have exactly 100 ohms, you know, anywhere probably from about 82 to 160, 200, something like that's going to work in there. And then coming down this side, we've got the transistor right there. Coming out this side, we've got R5, which is going to be a 56 ohm resistor. I may have given you a 47 ohm resistor. I may have given you a 10 ohm resistor. I might have given you an 80 ohm resistor. The value in here is not all that important. What this is doing right here is it's just limiting the current flow to your speaker. Okay, so you want some kind of resistor in there so you don't have a direct short through the speaker because speakers can be pretty low resistance. And if you didn't have some resistance in this section, when this transistor turned on, electricity could flow down right here and have almost a dead short to ground with nothing to block the flow of current, meaning your transistor would carry a lot of current, causing it to give off smoke. And you know, electronics, as you know, run on smoke. And if they let out the smoke, you have to put the smoke back in before they work again. And it's really hard to get the smoke back into a transistor. So there we go. We've got a resistor right there. And then for our class, we've got the big bad breadboard board where we have a speaker hooked in right here. And so that I can fit my speaker on, plug it into my board, what I've done is I've taken a couple of little wires and just slid them right in that terminal right there. And just to make sure they stay put, I actually cut the leads a little bit long, and you can see I popped them out the other side and folded them back so I can actually tug on that, and gave myself enough space that I could plug into most places on the board without too much problem, but not so much that it's going to flop around and get caught on things. So there you go. You've got your speaker, and we're going to do something with it right now. Hopefully in a few minutes, you'll be really, really annoying with that speaker. Okay, so there's all of our parts right there. I think, oh, maybe I forgot to mention our 2.2 microfarad capacitor right down here. Now this one says 2.2 microfarads on the side. Sometimes when we're writing capacitor values, we'll do a little bit of shorthand. So we'll do it for resistors too. And let me just make a note of what we might write as shorthand for some of these capacitors. So if you've looked at a schematic, if I'd written 2.2 microfarads on a schematic, like it's really easy for me to write 2.2 microfarads by hand, and I've got lots of space, and you can definitely see the decimal point right there. But if I'm putting that on a schematic, and you think back a few years when the photocopiers weren't quite as good and you were making photocopies of photocopies, you wanted to make sure that people didn't make any mistakes. And when you started using computers instead of doing handwritten stuff, getting that mu symbol in there, I mean, you can do it, but it's a pain in the butt. So we simplified a few things. So you'll often see like a 10 microfarad capacitor just referred to as a 10U capacitor. Okay, that does not mean IOU. That is 10U. There we go. So we've got a 10 microfarad capacitor. We could call it a 10U. So in the 2.2 microfarad capacitor, instead of writing 2.2U, what we do is we write 2U2. Okay. And the purpose of doing that is that the U is a lot more visible than that decimal point. So if you're making photocopies of photocopies, then then you're good. Nobody's going to miss the U sitting right in the middle, but sometimes a dot might show up or a dot might disappear when you're using older photocopying equipment or getting bad image compression on the internet, whatever the problem is. So we'll use this mechanism to refer to our capacitors. You might also see something referred to as a U22 capacitor, and if you see something that's U22, that's going to be 0.22 microfarads. Okay. Yeah, we do the same thing with resistors, right? Because a 10 ohm resistor should look like that. Okay. But really, finding the ohm key on your keyboard is difficult. So we'll write that as 10R. And if it's a 10,000 ohm resistor, we'll write that out as 10K. Okay, because finding that is really hard and doing this is really simple. This also means that I'm okay. I am, really. A bit nuts at times, but okay. Speaking of that, let me just pause this for a moment. I'll be right back. Ah, the beauties of the recorded lecture. I can stop in the middle of it to take a text from my wife and not be incredibly rude as I would if I was to do that in the middle of an in-person lecture. And you don't even notice because I pressed the pause button. At least I hope I pressed the pause button. Okay, so we've got all our parts laid out here. We've talked about switch names and switch types, and we've talked about capacitor naming and capacitor types, and we've talked about some different values that we could throw in there. I guess it's time to start getting ready to put them onto the breadboard. So I'm just going to slide this out of the way, and I should have cleared more space on my desk. And here we go. The magnet on the back of the speaker likes to pick things up. So if you swing it over top of your electronic components, take time to wipe it off before you scratch your table or anything like that. Okay, here we go. We've got our Winky Blink that I just built a little bit earlier, setting right up in here. Now I'm going to follow this schematic, and I'll zoom in here a little bit. I've got a schematic on the right side of the screen there so that we can follow along with that. And I'm going to start over on the right-hand side of the schematic where the power comes in. And let's just draw a little line. It's coming up right here. It's going to come up along through the switch, okay, and into the system right over here. So I'm going to connect to my red power line right in here, and I'm just going to jumper that down into the board. Now, a couple of rules that I like to have my students follow when breadboarding, and I won't say they're necessarily universal rules, but I think they're pretty good ones, is use a red wire only when you're connecting into the positive power line, and when you connect into the positive power line, only use a red wire. When you connect into the negative power or ground line, only use a black wire. And when you use a black wire, make sure that it's only connecting to ground. That saves a lot of work with troubleshooting when you follow it. And it sounds like a bit of a pain in the butt to go through right now, but believe me, it will save you time in the long run. Also, you'll notice that I cut it so it's nice and neat right here. and you leave yourself about, like I say, about 1 centimeter of exposed lead right on there. 1 centimeter is about the right amount to get in there and grip into your breadboard quite nicely. Okay, now as we said on that switch, we're going to put the middle lead of our switch connected to that red line right there. Okay, and you don't have to do that with a switch. In fact, we could skip this entirely and just plug things into the main side right there. But if you've got the switch, why not? If you don't have it, don't worry about it and just sort of skip over this part. You'll see where I go next. Now, if I throw that switch on, okay, and I decide which direction do I want to be on, it could be this way, it could be that way. If it goes on, it's going to come in and I'll decide to go this way. So when the switch is in this position, I have now connected this row of 5 to this row of 5 right here. So I've jumped those two together. When the switch is in this position, I've connected this row of 5 to right in here. So just beware that if you're using a double throw switch, don't use this side for anything else unless you know what you're doing with it. Right now, I just want to be able to slide it in there to turn it on. And now my power is going to come out right in this row right in here. And that is going to be where I come up right in here, and I'll sketch that in, highlight that. Maybe I should use the highlighter right here instead of the felt pen to mark this up. And I'll take a yellow highlighter right here, and that's all running along right there. Now that highlighted line right in here tells me that I need the emitter of my 3906 and one of the leads of my momentary push button switch to connect into this line right here. Okay, so I'm going to grab my big push button switch right here because I find it stays in my breadboard nicer. And I'm going to plug it in right here. Now I have to jump across the board right here, and that's okay. But what is critical is that I find this line that the pin right here is sticking into, and I get one of these pins right in there into it. Then I just press that down into the board. You might have to rock it a little bit to get it to stay in there, and I think you'll find that stays in a lot nicer than the little ones do. But if you want, you can fit the little one in. It's just a little more awkward in this case to follow along because I'm using the big one and you're not. But if you're feeling creative, go ahead and give it a try. There's many ways to do a breadboard correctly. Okay, and let's find that transistor. That's the 3906. Double check to make sure it's the 3906. Lean it back and forth in the light. I'm holding it back here and making sure I get that shimmer off the 3906. And the emitter is going to plug in to that yellow line that I've just marked up on the schematic. And so the emitter goes into the same hole as all the rest of those things do. Now, if I just plug it in like that, I am going to have a problem, okay? Because you'll notice that my base is fine. It's not plugged into anything with any other pin, but my collector is plugged in now to the other side of the switch. So that's not going to work out very well for me at all. So I don't particularly like that setup. So what I'm going to do is I think I'm just going to move this down over here and give it its own space. In fact, if I lean in and look right here, I can probably put that in right there. And what I'm going to do is I'm just going to take a small jumper and connect from that line over to that line. And you may have to cut a piece of wire to do this. I just happen to have a few jumpers sitting around. And, you know, I can usually get this in with my fingers, but having a few little pokey things, having a pair of needle nose pliers around probably helps for manipulating some of these components. They do get kind of tiny. And at every step when you go along on the breadboard, just take a moment to double check and say, okay, I'm in this set of holes right here. That set of holes connects to my switch. and that set of holes comes back. And now, because of my jump right over here, it connects to this emitter, and that emitter, okay, is part of this circuit right here, but my base and my collector aren't connected to anybody else yet. And if you're doing that and following along, then you're probably doing just fine. Okay, now this switch right here, since we've jumped across the board right here, and these holes on this side aren't really connected to anything over on that side, we can do a little bit of juju down on this side too. So we can use the whole board. And I'm just going to highlight this next section that I'm going to wire up in green. Okay, and this one's actually pretty easy to wire up. So there's some green highlighting coming in there. And what I've got connected right here is I've got one pin of the switch, and I want to go to R4. And so I've got my R4 sitting there and ready to go. And R4 is going to come down here, and it's not going to ground. It's going to connect up to some other things. So I'm going to put my R4. Make sure I've got R4. Red, red, orange is 22K. And I'll plug that in right there. Now, with the Winky Blink, I'd actually made the circuit a few times the exact same way. This time, almost completely freestyling. So let's see how we go right here. So we've got R4 in there right now. And I'm going to highlight this section in blue. So I want to connect this section together right in here. And so there's three things that are going to be connected into this section. I've got R4 coming into that set of 5 holes already. Now I'm going to want R1 and C3. Well, C3 is going to be really easy to do because it goes down to ground right here. Okay, so that's this side of the resistor because we've come through the switch, through the resistor. Okay, this was all in here. That's what I've highlighted in green right here, where those parts are hooked together, right to there, right to there, and right to there. And what I've highlighted in yellow, or sorry, what I've highlighted in yellow is all on that side. This side is what I've highlighted in green right in here. And now what I've highlighted in blue is going to be all in this set of 5 holes. So I'm going to take my 10 microfarad capacitor and double check to make sure that it says, or is that 10? C3 is, 22. I'm taking my 22 microfarad capacitor. This is why they don't have me on NASA's mission control. And I'm going to plug that in right there. And there we go. Now I've got a nice little connection. I'm in on this side in that blue highlighted section, and down here I'm into the ground line. I'm just going to highlight that whole ground line in, I don't know, a nice big gray line instead of black right here. But this is all kind of black right here. This is my direct highway, my return route back to the battery for everybody down there. So all of these pieces right here are all eventually going to hook into that blue header because that all carries it through and right back out to the power supply or to the battery or whatever you're using to run to the circuit. Okay, let's come back up to our blue section right here and do a quick inventory. In the blue section, which is on this side of R4, I now have the capacitor right here, but I need to add the resistor R1, which is a 120K ohm resistor. And so I'm just going to pop that in. Where's that going? It's coming back to the base of the transistor on the other side. So you know what I'm going to do is I'm going to see, can I get that to stretch right across the middle of the board and connect into that base. Getting out a pair of pliers, just setting that up and going to put one side. Okay, so we're going to the base on one side right here. Okay, because you can see that now R1 is coming over to the base right here. And the other side of R1, small grippy things help. Tweezers. Tweezers are good too. make sure it's down and nice in there. Give it a wiggle. Make sure these aren't popping out. If you cut the legs too short, they might pop out and you might have to use a replacement part of somewhat similar value. Like I say, they don't have to all be the same. And pay attention to the fact that when you look down here, that this one, and this one are all in the same line because those are all of our little blue connections right there. And I go back to the base of the 3906. Wait, what am I talking about? Geez, I wish this thing had a rewind. That's not going over there. Stop! And after I lengthen it all, it goes to the 3904. You were probably wondering what was going on. I told you I was freestyling all this. Let's pop a 3904 in there. This is even easier. So I pulled that, sorry, just a minute. Where did that resistor go? R1 is coming in here. It's not jumping back to the other side of the board. R1 is coming in right here. I'll hook it up right on here. I was getting ahead of myself. That was the way I had it hooked up last time. I had a different arrangement and jumped back and forth from one side of the board to the other. Got all fancy. It was kind of fun, but not what I want. Okay, there we go. R1. Good thing you guys were paying attention and called me out on that. Thank you for putting up your hand and mentioning it. Lovely online lectures. Still get to make mistakes, but no one shows them to you before you make them. Okay, here we go. So this is right in here. R1, it has a value of, where's my R1? 120K. So I see brown, red, and yellow. There we go. That's looking a little bit better. Whew. Okay, coming off of there, let's highlight this section in right here. And this is all the stuff that is hooked up to R1. Notice a little bump in the line right there, meaning that we don't connect there. Usually that's an older style way of saying don't connect there. What the more modern style is that you'll just draw the true lines crossing, but you won't put a dot on it. So unless you see a dot, don't assume the lines are connected, okay? Only assume that two lines that cross are connected if you see an actual dot showing on them, like we have right here, okay? If there was no dot there, those two would not be connected, but there is a dot, so they are. So that's why I've highlighted that entire section in pink. Okay, now everything that plugs into the pink section right there is going to be connected in this step. Let's do R3 first. That's the easiest one because R3 comes from right there and just goes back to ground. So we can do just like we did with that capacitor. Excuse me, and jump that into ground right there. So that takes care of R3 for us. Comes from that connection to that connection. This set of 5 is kind of our purple set of 5 right now. And then we've got a transistor that goes in there, and we want to connect to the base of that transistor. We want that to go in right here. And so I'm going to pop that in about like so. So looking at that, the flat side is pointing towards my pencil right now. So we've got the emitter in this row. It's not connected to anything just yet. We'll hook it up soon. The base is connected right here. So that's in that whole pink line that we've got set up. And our collector isn't connected to anything just yet. Okay. And then what else do we have that's going to go in here? Capacitor 2 is going to go in there. And that is our little blue friend right here. And let's take that. That's going to come off the base. We've got a few things in here already. This side of my board's getting a bit crowded. I'm going to jump back over onto this side of the board over here. So now in my purple line right there, I see R3, R1, the base of the transistor, and C2 all plugged into there. So if you've got all of those plugged together and you check up that, then you're probably right there. Electronics is a pretty detail-oriented thing. If you've got obsessive-compulsive tendencies, you're probably having a blast right now, except for that part where I got it wrong. Okay, next we're going to connect an easy thing right in here while our emitter comes down to ground. So let's just put that right down to ground. And to do that, I'm just going to take a black wire and get it in here faster for you if I fit it in about like so. There we go. So this is the emitter. It's not the base or the collector, and it comes from there and right down into ground. So we've got that part done right there. And let's take a look at where our collector should go from right here. Well, the collector is going to be a fairly easy connection. Let's draw some orange lines right up here. The collector just comes up here and it connects to R2. And R2 is the resistor that I wanted to jump right across the board and send it back to the base. Okay, so find your emitter, your base, and your collector. And I can't quite do that anymore because of the way I've laid out the board. I'm just going to pop my R2 in right there and make sure I have it down nice and low so that those legs don't touch the capacitor's legs. Okay, so emitter, base, collector. Collector comes up here and that runs through R2, which is my 100 ohm resistor, brown, black, brown. That all makes sense right there. That was a fairly simple one to hook up. Okay, we've got a couple of different places where we can go next. Let's do easy things first. And it looks really easy to make a connection between R2 and the base of the Pnp transistor. And let's see, do I have a wire long enough to reach across there? I've got a purple wire all ready to go. I did it slightly neater and tidier last time. But since I've got the wire all ready to go, I'm just going to rebend the leads a little bit. You always want to keep your wires nice and neat and tidy. And that goes into the base of the 3906, and it connects to the 100 ohm resistor over here. Get in there, you little. There we go. Now, normally, I wouldn't be that happy with this connection because it's not the neatest piece, but I can come back and clean it up later on rather than obsessing about fastidiousness at this point. Just give it a little wiggle like you do with any component to make sure that it's being held in there securely, because you can get a wire that looks like it's in there, but if it's not all the way down in the bottom and it's not being gripped inside the holes in your breadboard, then it's not making an electrical connection, and it might look like it's there, but really the electrons don't know about it. What I don't like about this one is I've left a little bit of wire exposed. That's not very pretty. I should come back and clean it up later on. Okay, so let's move on to the other side of C2 right here, and I'm going to start reusing some highlighter colors because I'm running out. But this one's going to come in right here, and it's going to run across like that. That's going to come down and connect to C1. So what I'm going to see on this side, so find my C2 again, and I've got this row of 5. I've kind of covered up one of the rows with this jumper, but that should be okay. Let's do C1 first because C1 is really easy. C1 goes from that connection straight into ground. So make sure that the negative side of your aluminum electrolytic capacitor is pointing towards ground. You don't want them to be hooked up backwards. And make sure you get the ground line. It's sometimes really easy when you plug in to the headers right here to just plug it into the red by mistake, um, and double check that's in the same set of rows as C1. There we go. I'll just mark that off that we've made that jump to ground right there. Okay, now back in here at these connections, C2 comes into C1, and it also connects to R5 and to the collector of the Pnp transistor. So my collector is all the way over here, Eat Big Cookie, EBC, and it looks like I am going to need to whip up a quick jumper wire. Now you'll notice that I've already used a gray and a purple wire, so I'm not going to use another gray or purple wire. I'm going to cut a new one out of a new color so that if I'm troubleshooting the circuit and I say, hey, look at the orange wire, you'll know which one the orange wire is. This is going to be much more efficient once I find my wire strippers. There we go. So like I say, I like to come along here and I'll measure out roughly how far I need to go. Okay, so I need to come from, this is the connection of where C1 is going to ground. So this is going to plug in about right here. It's going to come over and plug in about right there. So I'll put a little bit of a mark on that wire. Okay, then I'll take the wire up. I'll give myself about an extra centimeter on the end when I go to cut that off. That look like about a centimeter. No, it looks like 10 millimeters. You just told us not to use centimeters because engineers don't like them. And there we go. We'll cut that off. When you're preparing any recorded lessons for your students, as a project, if you have to do that at UBC or something like that, try not to distract them as much as I do. I don't know if that's a really good example. Okay, so that is going to go from the collector, and there's nothing else in that collector hole. You can double check that over to right there. And that is a little bit more how I like my jumpers to look. Less like that, more like that. Okay, it's pretty fine detail. Let's see. So what have we got in there? We've got the collector connected. Should put a little yellow line on there saying that that's connected. Oh, we got lots of things coming in here too. This is where it's nice to go over and double check. We've got R5 is also coming out of there. Gee, we're almost done. So R5 is my last component to go into the board, and R5 is going to plug in right where that goes together. Let me just rebend R5. Sometimes the legs, when you plug them in and unplug them, get a few extra little kinks in them. But it's nice to have some pre-bent resistors ready that are just the right size to pop into the board. And so right here, where I come in off of C2, so just looking at this schematic, I've got C1 connected right here. I've got a connection to the collector of the 3906. And now I've got a connection to R5. So let me just highlight that in, make sure I mark that up that we've done that. And so it looks like we've got most of this circuit up and running okay. And now I've got my leads from my speaker, and you can see that the speaker connects between R5 and on my board. I'll just plug that in right there, and ground, and I can plug that other line into ground anywhere where I want on the board. The wires aren't quite long enough for you to see where I'm connecting. Let me plug it in right there. And now we get to see whether I can embarrass myself twice in one circuit or in one video by getting it wrong, by grabbing my power supply, moving paper out of the way so I can get to my power supply, stripping some ends off so I can fit my power supply into the board. My LEDs should start blinking when I do this. on the power supply. I have blinkage. I have an on-off switch right here. I'll slide it over to the on position. I have to get close to the speaker so that sound comes through. Oh, I guess I didn't have to get that close. Sorry. And that's about what you should be hearing. So what's happening when I push the switch right here, S1 gets pushed, and then electricity comes down here, charges up C3. C3 energizes the circuit. And when it's energized, these two transistors work back and forth, and they keep turning each other on and off because of the capacitors causing timing, just kind of like on the Winky Blink, a little more complex. And that results in a pulsed signal coming out down here. And as we pulse that signal on and off, it sends an electrical signal through the coils of the speaker, causing the diaphragm of the speaker to vibrate up and down, creating a lovely noise. Now, you can do some interesting little tricks with this. For instance, get it working first. Just if you've got it working good, and don't want to mess with it, that's fine. But there's times and places to play around a little bit because, like I was saying, when I press that button, it turns things on over here. You can also take a jump from the anode of one of your LEDs on your Winky Blink and run that right in here to the other side of the switch. And now every time it blinks, it turns it on. It's like pushing that button. I don't generally like using jumpers like this for permanent things on the breadboard, but for temporary little things like that, they make life pretty easy. So if you've got a few of those, maybe they came with a breadboard kit or something like that, they're pretty useful. I'll try not to use those for general breadboarding because this is a much neater way to lay things out. What else can we do on here? Well, I told you this capacitor down here, C3, was responsible for how long it would take that siren to sort of decay on there. Now we've got C3 is set in there right now as a 22 microfarad. You could pull that capacitor out and you could put a 2.2 microfarad capacitor in there. And now you can hear that the siren doesn't last nearly as long because when this capacitor is charged up, it's only got 1/10 of the capacitance, so it discharges 10 times faster. Going the opposite way, you can take a bigger capacitor. Oh, what have I got right here? A 470 microfarad capacitor. You can plug right in there. Oops, don't plug it into the positive side. Hope I didn't toast anything right there. Oh, there we go. That one takes a while to charge up. You have to hold the button down. And then when you let go of it, hang in there. Get a good. It's still discharging. This capacitor still has charge on it because it's so big you can hear it discharging now. And it's still discharging. Capacitors have a discharge curve that comes down really rapidly at the beginning and then smooths out. So this last little bit was going to take a while. I don't think we want that in there permanently, but it's fun to check things out. So that's working pretty good in there. I'm going to put my original one back in here, make sure that's still working. Now, our little capacitor in the middle right here, that one is C2. I was saying that one's quite a bit involved in the frequency, and it's a really tiny capacitor. We've got some other low-valued capacitors in your kit. So for instance, this one right here says 103 on it. So 103 would be a 10 nanofarad capacitor. So it's going to be a smaller value capacitor, should charge and discharge more rapidly, vibrate more rapidly. If I pull that out and put a 103 instead of a 223 valued capacitor in there, you can hear the higher pitch that's happening in right there. Actually, that one sounds pretty good as far as sirens go. Right, so you can play with different values and put some different ones in there to get the sounds that you happen to like. You can also put a larger capacitor in there. So here's a 224, which is a 220 nanofarad capacitor. And if I drop that in there, you can hear that cycle time takes a lot longer to charge and discharge that big capacitor in right there. So that's what you should be getting off of here. Drop that right back down into there. And yeah, that's enough of that for now. Okay, you've got a siren. You've got a winky blink. You can link the two of them together. In fact, if you change the timing on your winky blink and make one side blink slowly, you could set this up so that you would have, you could get it in timing so that your winky blink controlled the timing here and you get and it would just go on forever, and you could leave it set up and running with a sign saying school project, do not touch, and then go out for a nice walk while your family sits around the house just seething at you. Or roommates. Nah, don't do it to your roommates. Your family might actually forgive you. Okay, there we go. Winky blink and siren.